Hello everyone. I'm Adithya Rajan from the Johannes Gutenberg University Mainz in Germany. And today I will be presenting our latest work titled Revealing the Higher Order Nature of the Hall Effect in Noncollinear Antiferromagnet Manganese Nickel Copper Nitride. And a preprint of our work has been published on arXiv. So this is the overview of my talk. First, I will introduce noncollinear antiferromagnets and motivate why they are interesting materials to study. And then I will briefly introduce anomalous Hall effect in these materials. Then we will move on to the results. First, the magnetic field angular dependence of the anomalous Hall effect and what we can learn from them. And lastly, but most interestingly, an observation of additional contribution to the Hall signal that we observe. So let's go. Non-collinear antiferromagnets are compounds with vanishing dipole magnetization, but unlike their collinear counterparts, they do not have antiparallel arrangement of spins. So in our case, for example, you can see that the manganese atoms have spins arranged in a triangular fashion in the 1-1-1 plane, which is marked. An important consequence of this spin arrangement is that they have a non-trivial magnetotransport properties like the anomalous Hall effect. And within non-collinear antiferromagnets in manganese nickel nitride, it is very sensitive to strain, and it has been shown that it has a linear relationship of its magnetic properties with the applied strain. So these properties make non-collinear antiferromagnets potential candidates to study for application in spintronic devices and sensors. Now I will briefly introduce the anomalous Hall effect. The Hall effect was first observed way back in the 19th century when a transverse voltage was measured on application of a current and a perpendicular magnetic field. Later, it was found that this effect is enhanced when the material is a ferromagnet, and in fact, it's not even necessary to have a magnetic field. And for a long time, it was thought that a net magnetization is necessary to have anomalous Hall effect. But in a major breakthrough in about 10 years ago, Chen et al. Predicted anomalous Hall effect in non-collinear antiferromagnets. This was subsequently experimentally demonstrated in manganese 3 tin and later in other compounds like manganese nickel copper nitride. A non-zero Berry curvature is at the heart of anomalous Hall effect in non-collinear antiferromagnets, but there have been other frameworks to understand the anomalous Hall effect in these compounds, like the magnetic octopole moment. So here I would like to explain the anomalous Hall effect switching using magnetic octopole moment. So here you can see that if we apply a large magnetic field in the -1, -1, -1 direction, if you look at the spin structure from the 1-1-1 direction, this is what the spin structure looks like. The manganese spins are all arranged in an all-in fashion, and this results in a net, a very small magnetic dipole moment of milli-mu Bohr range, and also a magnetic octopole moment in the same direction. Now, when we apply a magnetic field in the opposite direction, we see that the spins are arranged in an all-out fashion. And this, of course, results in the change in direction of the dipole and magnetic octopole moment. So this is how the spin structure behaves in response to magnetic field, which then results in switching of the anomalous Hall effect. But because the dipole moment and the octopole moment are aligned in the same direction, it is difficult to disentangle the effects and their contribution to the anomalous Hall effect. One way out is to apply magnetic field in plane so that the dipole moment is forced in plane, which then does not contribute to the anomalous Hall effect, which is exactly what we did. We grew manganese 3 nickel copper nitride oriented along with its 1-1-1 axis out of plane. And then we applied magnetic field in plane while simultaneously measuring the anomalous Hall effect. We carried this out for a series of angles and plotted the antisymmetrized Hall resistivity at 15 Tesla. And this is what we find. So we can clearly see that the signal has a periodic behavior. And if we use a sinusoidal fit with a periodicity of 120 degree, it results in a good fit. So how can we understand this periodic behavior of the anomalous Hall effect? We used a combination of symmetry analysis and DFT calculations to find that the octopole moment prefers to align along the 8 equivalent 111 directions of the crystal structure, which you can see in these two images. And if you see from the 111 direction, like in this image, one can start to see an emergent 120-degree symmetry. So if we now look at the place where we have maximum anomalous Hall signal, this occurs when we apply magnetic field in this direction, which then results in octopole moment aligning along this red vector, like this. So because this has an out-of-plane component to the plane of measurement, we observe a maximum anomalous Hall signal. Similarly, when we apply a magnetic field in this direction, the octopole moment aligns like this red vector, which then has a negative out-of-plane component, and it results in a negative, in a minima of the anomalous Hall signal. So similarly, we can go on, and now we see why we have a 120-degree symmetry. So we can have two takeaways from this result. One is that there is a conclusive evidence of anomalous Hall effect originating from the octopole moment, because there is clearly no effect of the dipole moment on the anomalous Hall effect as it's in plane. Secondly, the 120-degree symmetry of the anomalous Hall signal is due to the symmetry of the octopole orientation. So before I showed the angular dependence of the Hall signal, but in the process, we observed something even more interesting. So when we did field sweeps of the anomalous Hall effect, we found that there are some interesting features. For example, here, the field was applied along this angle, and we observed that the maximum of anomalous Hall signal is not at the saturation value, as we would expect if the signal was solely coming from the octopole moment. So now what we decided to decompose this signal into octopole component and the rest. To fit the octopole component, we used a hyperbolic tangent function, and the additional contribution we fit using a Gaussian function. And surprisingly, it was a very good fit. So you can see this is the Gaussian, this is the hyperbolic tangent, and this is the Gaussian. And we repeated the process for all angles. And for example, here is another example. We see another non-trivial feature here, which we again fit with a combination of hyperbolic tangent and a Gaussian. So what exactly is the source of this additional Gaussian feature? To make some intelligent guesses, let's look at the representation theory of the antisymmetric anomalous Hall conductivity. So these are the leading non-zero terms that contribute to the anomalous Hall effect. The first one is the magnetic dipole moment, which we have essentially eliminated because of our geometry. The second is the magnetic octopole moment, which is maximum when all the spins are aligned in the plane. And we also have a scalar spin chirality, which is non-zero when the spins are canted out of the plane. So to probe this aspect more, what we did was to plot the additional Gaussian contribution as a function of the magnetic field angle. And this is what we found. So the blue curve represents the Gaussian contribution, and the red curve represents the octopole contribution of the Hall effect. And what we can immediately see is that they have the same symmetry of 120 degree. And but more importantly, the octopole contribution and the Gaussian contribution have opposing signs of the Hall coefficient. So this gives us a hint of that these spin orders have the same origin, but are of competing nature, which is why they have a different sign. So now what we did was to theoretically calculate the anomalous Hall contribution of both the octopole moment and the scalar spin chirality. And this is what we found. Here again, we see that both these contributions have a 120 degree symmetry, but they have an opposing sign. which is in a good agreement with our experimental observation. So this shows that our hypothesis that the additional Gaussian contribution in our Hall signal comes from scalar spin chirality is on solid foundation. With this, I would like to summarize my talk. We first observed anomalous Hall effect in manganese-3 nickel copper nitride with an in-plane geometry, showing that octopole moment indeed is the source of anomalous Hall effect. And in the in-plane field angular dependence, we saw a 120-degree symmetry. And we explained the symmetry using the symmetry of the octopole vectors along the 111 plane. And additionally, we found some interesting features in the field sweep of the anomalous Hall effect. And the angular dependence of the additional contribution and the octopole moment have opposing signs with the same symmetry. And we believe that this additional contribution comes from the scalar spin chirality. With this, I would like to thank my funding agencies and all our collaborators who helped in pushing this work through. I would then thank you again for listening, and now I'm open for any questions.
Thank you very much for your very detailed presentation, Adithya. Floor is open for questions. You can write them in the chat or just raise your hand. I cannot see any hands, so I can start maybe. A bit of general question. What will be the next step in your research? Is it this insight about anomalous Hall effect on these materials leads towards some possibility of new devices, or
yes.
So can you maybe elaborate on that?
Yes, I think so far the primary reason for doing this work is fundamental research. But of course, there have already been studies shown in manganese 3 tin, which is a similar material, which is also a noncollinear antiferromagnet, where it has been shown that we could possibly use it for a device. But because the nail temperature of the compound that we use is below room temperature, it is not ideal. But there are similar materials of this class whose nail temperatures are above, let's say, 350, 400 range. So those materials, it would be ideal to probe, to be used in a memory device, let's say. And because we see that there are so many different contributions to the Hall signal, so we can fine tune how we would like to use this material as either a sensor device or a memory device.